It's the wavelength at maximum wavelength? Or is it the maximum wavelength? No, it's not the maximum wavelength. It's the wavelength at maximum absorption. And so the maximum absorption is, we look at the top of this peak here, and this will be our lambda max. Our lambda max looks like it's about how many nanometers, roughly?
About 600.
About 600 nanometers. And so, in other words, visible light is going to range from 400 to 800, roughly. And so 600 is right in the middle. And so we're going red, orange, yellow, green, blue, indigo, violet. It's in the green-yellow range, right? Around 600. And so lambda max is green-yellow. Here, we're absorbing or we're moving that color out of the rainbow, which means the other colors are going to add up to the opposite side. All right. Do you guys remember Beer's law?
Yeah.
Yeah, so let's take a look at Beer's law.
I thought we were doing the rate law now.
We are.
Thermokinetic.
We're doing the rate law lab, but we have to review all these Chem 1A concepts to do it. The rate law. Beer's law says that the absorbance, which is this, what do absorbances typically range from?
I'm sure in our same page. Oh, what do you mean, babies?
Not.
No, we're looking at the nanometers.
We're looking at the y-axis.
Yeah, according to that, somewhere probably less than 2. I don't remember using that.
Beer's law just says this, that absorbance is equal to constant times the concentration.
Oh, yeah.
In other words, y is equal to mx. It's just linear. And so if we do a Beer's law plot, we plot A, the absorbance on the y-axis, and the concentration on the x-axis, and it should be linear with a slope of m, whatever that constant is. But Beer's law fails at high concentration or fails at low concentration? Beer's law will fail at very high or very low concentrations. Well, very low because, well, it doesn't really fail. It's just too hard to detect. You know, very low concentrations, you have to have ultra-sensitive instruments. Beer's law fails at high concentrations. It goes nonlinear. And so this is the nonlinear region. This is the Beer's law region. The concentration depends on what you're looking at, where that failure point is. But the absorbance doesn't necessarily. What we're looking at is we want to keep the absorbances at around 1 or less. When we go above 1, we start to go into the nonlinear region. If you look at this absorbance here, this absorbance is kind of high. You know, it's approaching 1.5, which is in the nonlinear region. Okay? So we got to watch out because Beer's law is only for a strict range. And so if we're in the Beer's law region, then the absorbance is going to equal the constant times the concentration. This constant, we know what it depends on. The constant depends on epsilon L. What epsilon is called the molar absorptivity or the extinction coefficient. L is the path length of the cuvette. And so if we're in the Beer's law region and we cut the concentration in half, if we cut the concentration in half, what will that do to the absorbance? It should cut it in half. If we cut the concentration by a quarter, it should cut the absorbance by a quarter, right? And so let's say we're in the Beer's Law region, we cut the concentration in half, this peak is also going to shrink to half its size. If we cut the concentration to 1/4 of the original, the peak is going to shrink down to 1/4 of the original, right? As long as we're in the Beer's Law region. The Beer's Law region is going to range from 0 to about 1. We're above here. So if we're above, we're at 1.5 absorbance units. If we cut the concentration in half, the effect isn't 1/2. We're in the nonlinear region. And so what we got to do is we got to make sure we're in the linear region of Beer's Law plot. And then what we can do is we can measure the concentration by measuring its absorbance. In other words, we can monitor the concentration of crystal violet. And so this is what we're going to do in this kinetics experiment. In the kinetics experiment, we're going to look at crystal violet. Which is this. And so it's a long formula, so we'll just abbreviate it CVCl. And we're going to react it with sodium hydroxide. CVCl is violet in color, sodium hydroxide is CCS, and then we're going to make CVCl, crystal violet chloride. Oh, not chloride, crystal violet hydroxide, sorry. CVOH, this is CCS. And so what we're going to do is we're going to see the color fade over time. And what we're going to do is we're going to monitor it, you know. And so an easy way to monitor how much CV plus I have is to measure its concentration by using absorbance. Here. Okay, and so what we'll do is we'll monitor this reaction at intervals here. So after a certain amount of time, some has reacted, some more has reacted. Here, and some more. And so as the reaction proceeds, we're losing some of it. And so what we want to do is we want to monitor this and see. Now, this is different nonlinear versus linear. We want to see, is it curved like this? Or is it straight line? Like this. We want to see how it reacts. And so we're going to have to take data over time to see, you know, is the reaction getting slower over time or is the reaction steady over time? This will allow us to make predictions. You know, if we understand how things behave, for example, we can measure a little bit and then predict. So for example, let's say I wanted to see how long it takes milk to spoil. Well, if I know if it's a linear or non-linear, and then I fit this to some mathematical function, I don't have to wait 60 days or 90 days. I can just do a quick experiment, see what the
Spoil rate is.
Yeah, and then predict out here, where would it be? You know, that kind of stuff. And so this is why we are interested in kinetics. We want to make predictions about how things are going to react. And that's what we're going to do. And the way we're going to monitor the concentration is to monitor the absorbance. We're just going to keep it in that Beer's Law range and then see, you know, how it changes. Now, absorbance isn't exactly concentration. In order to figure out the concentration, I need to know what my slope is. And do you guys remember doing Beer's Law plot and figuring out the slope? Well, we're going to skip that. We're going to skip that because we're just going to use the extinction coefficient given on Wikipedia. Here, the absorption max is at 580 nanometers and an extinction coefficient of 87,000 molar to the -1 centimeters to the -1. And so by using epsilon here and the path length of our cuvette, then we can calculate what our concentrations are going to be. And so in this experiment, we're just going to monitor the absorbance over time. And so we'll set it up on Thursday. So you don't have to prepare too much because we're just going to set it up together. But just to give you an idea of what we're doing, this is it.
Wait, but we're going to do the actual experiment on Thursday too.
Yeah, we're going to do the actual experiment on Thursday. So I think that's the actual experiment is pretty simple to set up. We're going to use the spectrometers. You guys use the LabQuest spectrometers?
Are they square, the little square?
Yeah.
Yeah, with the square cuvettes.
Yeah.
We're going to use the same thing. And then we're going to set up an experiment where the LabQuest is going to measure the absorbance at certain time intervals.
But how many, what interval of time should we go by?
He'll tell us tomorrow.
Yeah. Well, we'd like to take very small intervals,
The better the interval, the better the math.
but we'll talk about it.